Hi, so I have with me two matrices here. What we are required to do is to find the eigenvalues as well as the eigenvectors. Okay, so I'll try to simplify everything that I'm doing right here, but I'll try to explain. Maybe there are some parts where I might use some. I might use some concept. I'll try to explain where it is coming from. Okay, so when it comes to you getting your eigenvalues, okay, to get your eigenvalues, all you have to do is just to do what, find the determinant. Okay, the determinant of a matrix. But do you really go straight forward by just saying major diagonal minus minor diagonal? We don't do that. So what we do is that to get the determinant, we are going to say determinant, or just say det of matrix. Let me say this is matrix A. We are going to say minus excuse me, I'll say lambda here by I is equals to 0. So this lambda here is what is my eigenvalue. Okay, so in different textbooks they use different symbols to represent the eigenvalue. It might even be an arrow or anything, but I've already started to say my lambda in this case is my what, is my eigenvalue. Okay, so now this is actually the way we are going to get the determinant. So it seems pretty confusing, but this I right here is not just an I like for decoration or something. That's an identity matrix. Okay, so well, what about our eigenvector? Okay, to get our eigenvector, what you're going to do is that after we get the determinant, okay, from the determinant we're going to get the eigenvalue. Then for that respective eigenvalue we're going to get our eigenvector, and how it's going to be written is like this. For example, let's say excuse me, after solving for the determinant I find two eigenvalues. Okay, let's say I have lambda 1 as well as lambda 2. So if I get this eigenvalue, I want to get the eigenvector. I'll come back and say I have my A minus lambda 1 by I multiplied by, I'll say eta 1 is equals to 0. So this eta here is I'm using it to represent my eigenvector. So sometimes you find that they're using V here. There is no harm in you using any other symbol or any letter. It's okay as long as you have indicated to say that letter that you have used, it represents the eigenvector. For me here, I've used the mathematics symbol eta, which represents my eigenvector. Okay, so let me now try to come up with the determinant. So you're going to find that to come up with the determinant here, you're just going to say it will be your 5 minus your eigen value, which is that. Then you have your 9 here, then 2 minus 2 there, then minus 6 minus lambda there. This is equals to 0. So you might wonder to say, where does this come from? Of course, it's not really, it might waste your time to write everything step by step, but let me just show you where it is coming from. So if this matrix that I have here, if it's matrix A, for example, I'll say A is equals to my 5, then 9 there, minus 2, and minus 6 there, like that. So one thing that you observe is that this matrix A, I'm subtracting lambda, okay, by I. What is I? I is just my identity matrix. Okay, I is just my identity matrix. For in this case, that's a 2 by 2 matrix, so that would be like 1 0 0 1. Okay, so that would be like 5 9 minus 2 minus 6 there, like that. So you can distribute that lambda inside. That will be lambda 0 0 lambda there, like that. Okay, so I have to multiply by everything, but where there is 0, it still remains to be a 0 anyway. So you can actually subtract these two matrices. Okay, so this is just going to be term by term. Okay, so that would be 5 minus this one here. Okay, that would be 5 minus lambda. Minus 2 minus 0 is minus 2 minus this 0 here. Okay, so that would be minus 2. You do the same to 9. 9 minus 0, that would be a 9, minus 6 minus lambda, like that. That's where this one is coming from. Okay, So you don't really have to show everything that I'm showing right now, but you can just go ahead and write that step where, so right here you can just multiply the major diagonal, okay, then subtract the minor diagonal. So for the major diagonal, this would be like 5 minus lambda, then minus 6 minus lambda there, then that would be minus 9 multiplied by minus 2 is equals to 0. So this is going to be, you can expand this, that would be minus minus 30 minus 5 lambda plus 6 lambda there plus lambda squared plus this one is going to be plus 18 is equals to 0. Okay, so let's look at what this one gives us. So we have like lambda squared, then have like minus 5 lambda plus 6 lambda, that would just be plus lambda there like that, then minus 30 plus 18, that would be minus 12 is equals to 0. Okay, so that's a quadratic equation that we have. We can solve for r, sorry, you can solve for lambda there. Okay, so to find for, to solve for lambda here, I just have to find the product, and the product and this the product I have is, the product that I have is minus 12, then the sum that I have is the coefficient of lambda, which is a 1. Okay, so the question is what do we get? Okay, so when you solve here, it so happens that your lambda 1 is equals to 3, your lambda 2 is equals to 4. So that I'll just simply factorize that one there. It's more like you say lambda squared, you're looking for two numbers, you multiply them, you get minus 12, you add them, you get plus 1. That number is simply minus 3 and plus 4. So this would be like plus 3 lambda minus, no, not like that, minus minus 3 lambda plus 4 lambda there minus 12 is equals to 0. That would be like lambda there minus 3, then we say 4 lambda minus 3, like that. So you observe to say you have actually this is going to be minus 4. Yeah, that would be minus 4. It's good I have done this. So that's why I'm getting those two. Okay, so what I'm going to do right now is that I'm going to have to solve, I'm going to have to find the equivalent eigenvector for each eigenvalue, and I might only do for one. You can try to do for the other one or you can check the link of the PDF in the description below where I solved everything. Okay, so here let's try to use this one to get our eigenvector. So this would be like we are going to, we remember I said it would be like a minus lambda I multiplied by eta there. So since this would be 1 and that would be 1, we say is equals to 0. So at first, remember I said 5 minus lambda like that. So you just have to substitute with lambda there. That would be 5 minus 3, which will give us a 2 like that. Then here we still have minus 2, we still have a 9 here. Then we say minus 6 minus 3, because I'm using a 3, that would be minus 9. Okay, that would be minus 9. Okay, like that. So for me to what I'm going to use here you're supposed to have like your eta 1 here. So what I'm going to do for simplicity purposes is that I'm going to write my eigenvector in terms of like a column vector, and I'm just going to use x1 and x2, and this will be equals to 0 and 0 here. Okay, so we can actually just multiply row by column here. So that would be like 2 by x1 minus 2 by x2 is equals to 0. Then for the second part, that would be 9 by x1 minus 9 by x2 is equals to 0. So don't solve this simultaneously. what you can do right here is just to pick any of them. Like this is equation 1 and that is equation what? Equation 2. So what you can do is that you can you can just solve for let me pick the first one. So if I pick equation 1, that would be like one thing that you're going to observe is that your x1 is equals to x2. So let me just pick numbers for myself. Let's say you say x2 is equals to 1, meaning even x1 is equals to 1. So one thing that you observe is that your eigenvector 1, like eta 1, is just equals to um, this notation right here where I have that's a column vector. Then your x1 you say it's a 1, your x2 is also a 2. Sorry, your x2 is also a 1, and this is your what? That's your eigenvector for this eigenvalue here. Okay, you can actually do the same for this one. You can going to find your respective or the equivalent eigenvector. Okay, and that's how we solve that one. Let's look at the second part, which is our B. Okay, look at the second part, which is B in this case. Okay, so all the same here, just a matter of finding the determinant. So here for the determinant, you're just going to say 0 minus lambda. That would be minus lambda here, minus lambda. Then you have your 3 minus lambda, like that, and this is equals to 0. So that would be major diagonal. We're just going to get lambda squared plus that would be plus, because of this minus here, that would be plus 9 is equals to 0. So that would be lambda squared is equals to minus 9. So lambda is just going to be equals to plus or minus 3i. When I'm getting the 3i, the square root of 9 is a 3. But because there is a negative, that's going to be a complex number. So it simply means what we have is a complex solution. Okay, it's a complex solution. So you can actually use this as well. Okay, so the fact that you have gotten complex roots, it doesn't change anything. Okay, it doesn't change anything. So I can actually now choose to say let me use lambda 1, which in this case can be minus no, let me use positive, which is positive 3i. Okay, so what you can do here is just to come back and say, okay, I'm not, this is my eigenvalue, so let me use this eigenvalue to find my eigenvector. Okay, so this would be like minus my eigenvalue, that would be minus 3i. Then here you have minus 3, then here you have your 3, then minus 3i, like that. Then here supposed to multiply by the eta, which represents the eigenvector, but just multiply by the column matrix, which is going to be x1, x2, and this is equals to 0 and 0 there, like that. Okay, so what you're going to get here is that that should be when you solve for those, that would be minus 3i x1 plus 3x2. This will be equals to 0. So we say minus 3x1 for the bottom part. Then this is going to be minus 3i x2 is equals to 0. So I can use any of these to come up with to find your value of x1 and your value of x2. Okay, so let me use the first one. Which is my 3 minus 3i x1 plus 3x2. Okay, so can actually, this is equated to 0, you're going to find that your x2 is just equals to ix1. Okay, so let's say for example x1 is equals to 1, meaning x2 is just going to be equals to I. So it simply means your eta 1 is just going to be equals to instead of putting x1 here, you're going to put a 1, then your x2 is just going to be I, like that. Okay, and that's what you have. So that's the eigenvector for this for the eigenvalue plus 3i. Okay, so what is interesting here is that you can actually prove your solutions here. Okay, so since I found to say my eigenvector eta 1 is 1, then I here on the bottom. So let me try to prove this. So what you can use to prove that your solution is correct is this, is that when you want to transform a matrix, you can get that matrix, let's say for example matrix A, you can multiply it by what? By its eigenvector. So instead of me doing this, I can actually multiply the eigenvalue by the eigenvector. Okay, by the eigenvector. Okay, so these two are supposed to be the same if what I found is correct. Okay, so instead of me transforming the matrix A by multiplying it by the eigenvector, I can get the eigenvector that I find, multiply it by the eigenvalue, then it's the same. So our matrix is simply 0, then you have minus 3, 3 there, 0. We have found that our eigenvector, let me use the what we have found, which is 1 and I here, okay, is equals to our eigenvalue that we used is positive 3i, positive 3i. Then our eigenvector that we have found is 1 and I there, like that. Okay, so you can actually write this as a what, as a single matrix. Okay, so one thing that you get, that you're able to observe, is that you can actually look at the order of the matrix to predict how the answer is going to be. So since this is a 2 by 2 and that's a 2 by 1, so that 2 and that 2 can cancel out, you end up with a 2 by 1 matrix. So like that would be 0 multiplied by 1, that would be a 0. Okay, plus 3 multiplied by I, that would be 3i. You go on the denominator, minus 3 multiplied by minus 3 multiplied by 1 is minus 3. Then 0 multiplied by I, that's just a 0 there, like that. Okay, let's look at the other part. The other part is just a matter of distributing what you have inside. That would be like your 3i by 1, that is 3i. Then 3i by I, that's going to be minus 3, because I is negative. I times I is negative 1. Okay, so to finish this up, you observe that 0 plus 3i is just 3i. Then minus 3i plus 0, that's just minus 3, which is equals to that. And that's true. That's how you can actually prove that your the value of the eigenvector as well as the eigenvector and eigenvalue is correct. And that's how we answer that one. Thank you very much for watching.